So I mean, the main thing that I would say is, uh, here, let me stop sharing this thing. Sorry. Jeez. Or hang on. Uh, Stop that thing. Yeah. Okay. So um, the main thing I would say is that usually you don't know like what the underlying distribution is that you're dealing with. You have no clue. That's, I mean, most of the time you're not going to be like, well, obviously the underlying distribution is exponential, or obviously it's like Poisson, or obviously it's binomial or something. You're just going to be gathering data, by polling or something like that. And you're not going to really know what the underlying distribution is. And that's a problem if you want to say anything with any kind of certainty. But what we're going to do is we're going to say, okay, well, I do know that if my sample is big enough, do you remember what the cutoff was for the sample to invoke the central limit theorem in any kind of obnoxious case?
It was 30, right?
Yeah. And if you know that if you have a sample size of 30 or greater, that's enough to tame even the most obnoxious distributions. And so long as you ask a question about the sample mean or the sample total, you know that you can assume that that thing has roughly normal distribution, even though you had no clue what the individual data values, how those were distributed. Those could have been, some wild distribution. It could have been exponential. It could have been binomial. Who knows, right? But if you ask a question about the sample mean or the sample total, you know that that's going to have the normal distribution, and we're going to use that to our advantage. In surprising ways, we're actually going to be able to say, okay, because X bar, which is the sample mean, is roughly normally distributed, we're actually going to be able to say with a fair amount of certainty, like a range for the population mean, something that we didn't know anything about. We'll be able to say the population mean with, I'm 95% sure it's no bigger than this and no smaller than that. And you can say certain things like that about other population parameters, like the standard deviation, for instance. So, but it's only because we can say that X bar and, other statistics that we get from our sample have a roughly normal distribution that we can say anything like that at all. So you'll see, we're going to do things called confidence intervals. I don't know, have any of you ever heard of a confidence interval before? Here, let me show you something. Watch this. So let me open up another tab here. You guys see this? I'm assuming. Okay, so if I go to like Rasmussen reports, let's see. Let's go to the daily presidential tracking poll. Look at what it says here. All right, so they actually took and said, and they just asked people, hey, how strongly do you feel about Trump? Are you, do you highly approve or, strongly approve? Do you approve? Do you strongly disapprove, or what's going on here? And they basically tell us what those numbers are. Like 33% strongly approve, 44% strongly disapprove, apparently. Okay. And then down here at the bottom, they give us some extra details about their polling. So here it is right here. They say daily tracking collected via telephone surveys of 500 likely voters. Right, so who does that tell you the population is that they're drawing from? It says 500 likely voters. So who's the population?
People with cell
Americans.
phones.
Yeah. Well, apparently it's likely voters. Like it's not just all voters, it's likely voters. Those are, and they probably determine who that is based on how, on who voted in the last couple of elections or something like that. Okay, so that's actually a pretty good pool to be drawing your data from. So that's the population. Obviously, we don't know everything about it. That's why we're doing this in the first place. But they get 500 likely voters, and I think they do a 3-day rolling average where they actually just add up those 500s, whatever the results were for those 3 days. And look at this right here. Here is the key. The margin of error, the margin of sampling error, look at this sentence right here. The margin of sampling error for the full sample of 1,500 likely voters is plus or minus 2.5 percentage points. And we're 95% confident in this thing that, we're 95% confident that the true population mean sits within 2.5% of these numbers that we reported up there. Where in the world, how could we possibly make such a statement? We don't know what the underlying distribution is. Well, guess what they have invoked here to make such a statement? What do you think they used?
The central limit theorem.
Yeah, they used the central limit theorem. They actually used the central limit theorem. And they're saying, well, we kind of reported this sample mean, and I know the sample mean is going to have an approximately normal distribution. Okay, and we'll see how all of this works together here. But that's what this statement means at the end. The 95% level of confidence has to do with the normal distribution and kind of going out to 95%. I think, didn't I draw a picture one time that said 95% of the normal data sits within 2 standard deviations of the mean? Did I draw a picture like that at some point?
Yeah.
It was like 68% is within 1, 95% is within 2 standard deviations, 99.7% is within 3. So that 95%, guess where that's coming from? It's from going out 2 standard deviations from the sample mean. Okay, so that's how we're actually going to get confidence intervals eventually. Okay, so we can do some pretty amazing stuff because we have the central limit theorem guiding us now. Yeah. What other questions do you have? Could the sample size be too big? Okay, so Ryan is saying, could the sample size ever be too big such that you could not invoke the central limit theorem? No, the sample size it's only going to become a better and a better approximation the bigger the sample size is, because we're not asking questions about individual data values. What do we have to be asking questions about to invoke the central limit theorem again? We can't ask it about individual data values. What do we have to ask it about? What does the central limit theorem apply to? Well, yeah, right. So Ryan says IID, right? Independent, identically distributed. Yes. But also you can't ask a question about an individual data value. It has to be the sample mean. The sample mean is the thing that has an approximately normal distribution. Okay? Or the sample total. Those are going to have an approximately normal distribution. And the higher the sample size you take, the more that sample mean distribution is going to look normal. Okay, it's going to look more and more and more bell-shaped the bigger the sample size is. That approximation just gets better. On the other hand, you can't let you start to get nervous if your sample size is too small. If your sample size gets too small, then you're like, oh man, I don't know if I have a big enough sample size to kind of turn this thing into a normal distribution or the distribution of X bar just yet. But if the underlying distribution for the individual data values was already pretty like symmetrical to begin with, kind of like the uniform was in that one example, then your sample size doesn't really have to be that big. You can invoke the central limit theorem pretty quickly. Okay, I think I invoked it in that example, even though my sample size was only how large at the end? What was it? Was it like 12 or something? I think the sample size was 12 and I went ahead and did it anyways. Okay. Why? Because I knew that the distribution was pretty symmetrical already. It was a uniform distribution. So it's not going to be too hard to control that thing, and the thing's going to start to mound up and become a normal pretty quickly. Okay. All right. What else? Other questions? Other questions?
I'm wondering what the difference is because you said earlier that not everything is normally distributed, but it seems like I'm not understanding it right. But with the uh, CLT, it's saying that when you do this on even exponential, it looks like a normal. Can you just explain to me uh, why it's everything is looking like a normal distribution?
Well, it's because, okay, so let's see if I can find this picture that I had in the slides. Let me see. Here, I'll find it. Just a sec. Oh. Um,
I think it was slide 4 of 14.
well, the picture I'm thinking of is this one. Hang on. Can't see what I'm looking at right now. Okay, so you see this picture right here? So this is the distribution. Like suppose this is the distribution for the beginning. You see this kind of skewed, off-centered looking thing? You know, it's kind of shoved over to one side. You know, this might be like, you know, an exponential distribution or something like that. But that's the one for individual data values. Like if I just sampled 1 point, this thing right here would represent the probabilities of me sampling 1 point. But when I have X bar, how many points am I sampling, Timothy?
30?
Well, yeah, at least 30, and I'm computing their average. Does that make sense?
Yeah.
X bar is like I'm adding all of those individual data values together and I'm dividing by 30. I'm computing their average. But what that's going to do is it's going to take like really big values and really small values, and those things are going to balance each other out and tend to hunker down around the middle more. So like I might end up with a really high number and a really low number that just balance each other out. So do you see how that's going to kind of tame the overall distribution if I add all those together and compute their average? It's
Yeah.
going to start to make this thing look a little bit more normal. And then the more points that I take from this starting distribution, the more balancing is going to occur. And the thing is going to start to really kind of mound up and start to spike up around the mean. And it's going to like really start to look like a normal distribution the larger that n gets. Now to rigorously prove that would take a little bit of effort. You would have to take a class in like advanced probability or something. But does that at least make sense, Timothy? Like what's going on here?
So you're just averaging the individuals and you're just squishing them into groups and then saying that looks approximately like normal, even
Yeah,
though an individual might not be normal.
it's a brand new distribution, right? Yeah, I got it from taking things from the original, but I took those in things from the original and I computed their average. That's still a random variable, but it gives me a new distribution. And the larger my sample size is, the more normal that thing starts to look. Does that kind of make sense, Timothy?
Yeah. Yeah, that makes sense.
Yeah. Okay.
So when you say X1, X2, those are all like individual samples, right? And
Yeah.
then X
Well,
bar would
they're
be,
individual data points. Yeah. So I'm like sampling from this original kind of messed up distribution, right? So X1 is going to be somewhere in here, X2 is somewhere in here, X3. But then I take all of those and I add them together and divide by n. That's the sample mean. Yeah.
yeah.
That's going to give me a new distribution. It's not the same random variable as just an individual thing. Yeah. And it's going to kind of balance everything out. And that's why you start to see this mound shape start to emerge. Okay. So that's what I mean when I say you need to ask the right question. You can't ask a question about individual data values. Why not? Well, well, because I don't know the underlying distribution. You understand? I don't know what's going on. So that thing I know nothing about. But the miracle of the central limit theorem says if I just take a bunch of them and take their average, that thing I do know stuff about. I know it has an approximately normal distribution. That's why over here, remember this problem, the very next one? When I knew what I could do if I took a sample mean of 40 things, yeah? If I took the sample mean of 40 things, I knew that I could invoke the central limit theorem. But the minute somebody asked me about 3 individual rivets, I couldn't answer that question. Why not, Anthony? Why couldn't I answer that question?
Because you only have the sample mean, not the individual, or you don't know underlying distribution.
Yeah, I don't know what that distribution is. I have no clue. So I don't know how to answer questions about individual rivets. I only know how to answer questions about a sample mean of rivets, because that allows me to invoke the central limit theorem. And I know, so it's approximately normal distribution. But with this, I don't know jack squat. I don't know anything, right, about that underlying distribution. So I'm unable to answer that question. That's why I did this example, was to kind of illustrate that. Hopefully that made sense. Yeah. Other questions? Other questions? All right, well, nothing else? You guys don't have anything else? Well, I think what I'm probably going to do, I realize that, man, I'm so messed up on my days right now. I realize that there's no class on Friday, apparently, right? It's like Good Friday or something. So I'll probably have you turn in the homework quiz on like Monday or something. That makes sense. And I gave you several problems in one of the chapters. Was that chapter 5 or something? Is that what that was? I think it was chapter 5 from Olowski Dean. I gave you several problems to kind of look at. Any idea when the test will be graded? Well, I already started grading it. Some of them are already graded. If you're Apparently you're not one of the lucky ones to have yours graded yet. Your grades are just going to appear as I finish them. It takes me a while to grade them, but I'm hoping to be done by the end of the week. When did you guys turn those in? Was that on Wednesday or something last week? Yeah. So I'll have those, I should have those things done hopefully by the end of the week for sure. I've just been kind of slowly going through and I'm typing feedback into the actual exam itself. Well, into the comment section in SpeedGrader, that's where it's happening, and you should get a notification once that thing starts changing in there. So hopefully that'll happen soon. Other questions? Other questions? Well, hey, thanks for dropping in. The homework quiz will be due next Monday. So I'm giving you a little bit of an Easter break here. And to circle back to Aaron's original question, we will be using the central limit theorem with reckless, well, not reckless, with abandon. Okay, we'll kind of jump in there and we'll be using it like crazy to do a whole bunch of stuff with statistical applications. The next place we'll go is something called confidence intervals, which is along the lines of what I just showed you for Rasmussen reports. And this stuff's very important for you to understand what in the world you're being told statistically by these media sources. You'll be able to read those things and say, oh, I see what's going on. 95% level of confidence, I know exactly what that means. Okay, so that's sort of a helpful thing to have in your cognition for sure. So that's kind of the plan moving forward. Then we'll finish the semester doing something called hypothesis testing, which uses the central limit theorem again to test certain hypotheses that you have. You think something's true? Well, how do I kind of try to prove something that I think is true, with high probability? Like I'm saying, this is really likely to be true. Well, how in the world do you prove such a thing? And we'll see how to do that with hypothesis testing using the central limit theorem. So that'll be the last topic that we cover in statistics. Okay? Hopefully things are going well for you. Good to see those that are here. Although the only face I actually see is Anthony right there, but that's all right. I see Madeline's face too, but that's just a picture. Okay. All right. So anything else before we take off here? Anything else?
Dr. Hammond, could I just ask you a personal question after class?
Yeah. Okay. Sure thing. Okay. All right.